Okay. Today in Chem 203, we're going to cover the Chapter 10 material to be tested on Exam 4. We've already covered Chapter 9. This is Chapter 10, Acids, Bases, and Salts. Acids, bases. Everybody has a rough idea of what an acid base is, but they think they know what a salt is. Now, when we say salt out in the kitchen, say, we mean table salt, sodium chloride. But in chemistry, salt means something entirely different. Well, it's related, but it's more expansive, covers more ground. A salt, in fact, is one of the products of the reaction of an acid and a base. That's chemistry definition of a salt. So let me share the PowerPoints here, there. Let's see. Okay, I can still access it from here. Wait, okay, just checking to be sure anybody can come in when they arrive. Can get in the meeting room. Okay, make a slideshow. Try it again. There we go. All right, acids, bases, and salts, and I'm rearranging some things here so I can see what I'm doing. All right. So we're gonna talk about the different types, the theories surrounding acid, bases, and salts. We're going to talk about strength of an acid base in chemical terms. Then we're going to look at equilibrium with acids and bases. And then react acids and bases with each other. And then there's a special nature of water. Since our discussion is going to focus on aqueous solutions, then we ought to know something about the solvent. And that's what this discussion is about. Then we'll go into some methods of making acids and bases more manageable, understanding them and how those methods can be maximized. Then we'll look at buffers. All right, everybody has an idea of what a buffer is. We're going to tell you exactly what a buffer is and how to make one. And then we'll finish off with what's an electrolyte, and then go into more detail about acid-base reactions that we call titrations. Okay. So the first viable definition in scientific terms of acids and bases came from a Swede named Svante Arrhenius. This was toward the end of the 19th century. His definition was very simple. He said, if you want an acid, you need to dissolve a compound. That's our generic acid. A compound that has a hydrogen on it that can be released into solution. Okay? So it would be and naturally, the positive goes with the hydrogen ion. They're generally positive. So it's actually it's a proton. Because, right, hydrogen has one proton, one electron for most of the isotopes. So that's why I'll call it a proton sometimes. Because you strip the electron away, what do you got left? Just the nucleus. Right? That's a proton. And since this positive, this is neutral, and these have to balance, right? Then you get a negative electron that was here is left with this part of the acid. Now in this case, in this example, the part of the acid that's left behind is the nitrate, polyatomic ion. So remember that negative charge is distributed over the entire ion, HNO3. It's not associated with one particular atom. His definition of a base said, well, now you need a compound with a hydroxyl in it that can be released into solution. And we know hydroxyls are a negatively charged polyatomic ion. Right, we learned those early on in the semester. And the charges, again, have to balance. And this polyatomic has that negative distributed over the entire molecule, the ion, excuse me. Okay, so that was Arrhenius' definition of acid and base. But they are created by two different processes. The Arrhenius acid, this right here is an intact, covalently bound compound. In other words, there's a bond between that hydrogen and acid part, whatever it is. So in order to break them apart, the Arrhenius acid has to undergo ionization. And for ionization, you got to add electrons or remove electrons. So in this case, the electron here is transferred to there. That gives you the negative and leaves behind the positive. That's called ionization. And the Arrhenius acid fits that definition. The other, however, the base, is really an ionic compound. Well, it looks like this before you put it in solution. Now, all it has to do is just break apart. It dissociates. And the Arrhenius bases fit that definition. Okay, so this is an artist's view. This comes straight out of your textbook of what happens when you dissociate versus ionize. But the takeaway from Arrhenius' definition is that the acid has a proton, has available from ionization at least one proton, whereas the base has available one hydroxyl to be released into aqueous solution. That's his definition of acid and base. And for most acid and bases, that works fine. That covers most of the bases. No pun intended. So which of the following describes an Arrhenius acid and base? An acid is a substance that produces hydrogen ions in water, and a base is a substance that produces hydroxide ions in water. Very simple. Scientists like simple. There is power in simplicity. All right. There was just a problem that eventually developed with Arrhenius' definition. Now, Arrhenius didn't work on acids and bases solely. He was into a number of different projects that we can't get into in this course because this is too superficial. But the acid-base definition from Arrhenius worked for most cases, but there were some cases where it didn't work. You could detect hydroxyls in the aqueous solution, but there were no hydroxyls in the molecule before you put it in solution. How do you explain that? Where'd they come from? One of those examples is ammonia. we put ammonia in water, and you end up with hydroxyls, right? Where'd they come from? Well, it took independently a Dane, Johannes Bronsted, and an Englishman, Thomas Lowry. They independently proposed a solution to that problem. And they said when something like this happens, it's not the dissociation of a hydroxyl that matters. It's the ionization process that is key. And in order to do that, you've got to introduce the solvent into the reaction. So when you put ammonia in water, it reacts with the water molecule, and one of these protons ionizes and is transferred to that ammonia molecule. Now, what does that leave behind? If this plus is going here, then it leaves a minus behind, correct? There's your minus, and there's oxygen, hydrogen, oxygen, hydrogen, hydrogen. So now what do we have? We've got NH3 plus a hydrogen ion, which makes the whole molecule positive. This covalent bond was broken to release that one, came over here and formed a new covalent bond with ammonia and produced that molecule. So that's where you get the hydroxyl in many cases. It's from the intimate involvement of the solvent itself. All right, so now the definition of an acid base has to change. Bronsted and Lowry, instead of focusing on hydrogens versus hydroxyls, they focused only on the hydrogens. Okay? Any substance that can donate a proton, a hydrogen ion, is an acid. So there's your proton that can be donated. So this is the acid. Right? It looks a lot like Arrhenius' definition. But a base is anything that can accept a proton. Right? And if we do this in water, water becomes the base. Right? Acid base. Whenever you get a reaction of any kind with an acid or a base, they always come in pairs. You can't do acid magic without a base. So if this is the acid, it's the proton donor. This is the base, the proton acceptor. So if we transfer this proton over here, what do you get? Well, you get that. That's the hydronium ion, derived from water. And then what do you have left over? You have that. Okay? So that's the real process that's going on in solution. And whenever you have an acid reacting with a base, I might be jumping the gun here, but this is stream of consciousness. The acid now has become a base. It can accept a proton, right? If it accepts a proton, now it's back to this form. So we call this the conjugate. Base. Right? The conjugate base is always on the product side. Acid base, conjugate base of this acid. So that base must have a conjugate acid. There it is. So now this is able to donate a proton. This is able to accept a proton, which means this reaction can run backwards. It can run both directions. Right? And it just depends on the nature of the acid relative to water as to whether it's going to be mostly over here or mostly over here. Right? That's a problem of equilibrium. Okay. Let's see. Which of the following describes a Bronsted-Lowry acid base? Acid donates a hydrogen ion to another substance, and a base accepts a hydrogen ion. So that definition incorporates Arrhenius, many of the things that Arrhenius proposed, but it goes one step further and engulfs many, many more circumstances that Arrhenius did not address. Right? It's like I've said before, when you have a theory and the theory fails to explain something, fails to explain a circumstance that gives a result, then you have three options. You can take your theory and restrict its use. Just say, all right, it's not going to work over here, so we just say, don't use it anywhere but under these circumstances. And that happens quite often. Or you can modify it. Make it expand, make it more complex and expand its use that way. Many theories do that. But eventually, those theories, if they go far enough, usually collapse. Or the third option is immediately discard that theory and substitute a new one. Now, it just occurred to me that maybe there's a way to hybridize. Bronsted-Lowry didn't actually take Arrhenius' definition and build on it, but if you apply Bronsted-Lowry acid-base definition to any acid-base reaction, it will work for Arrhenius type acids and bases. So maybe that's a fourth category. You hybridize. All right. So there we have our acid and our base. Water's the base in this case because there's your acid. Hydrofluoric acid transfers a proton to water, makes the hydronium ion, and the hydronium is now an acid. And the fluoride ion is the conjugate base, which means it can accept a proton. Okay, so how do we identify acid-base pairs? We call them conjugate acid-base pairs, which means you have an acid and then you have the base that's derived from it. Right? In those cases, two things have to be met. When you have comparing the conjugate base to the acid, the part that's left over in the conjugate base has to be derived from the acid. So there's the A and there's the A. That's the first rule. You got to meet that condition. The second condition is one proton at a time. Only one dissociation. So you have one proton there, it ends up over here. Okay, those two rules. So if you have something like sulfuric acid, and you say it reacts with water, and you say both of those protons are transferred. So what do you have? You have the sulfate, and you have two hydronium. Now that's a valid equation, but it's not an acid-base pair. It's not a conjugate acid-base pair. You have the sulfate here, but the sulfate is not the part that you want over here. because you have to lose one proton at a time. One proton lost would be HSO4 minus plus one hydronium. Okay? Maybe that's a way to detect a problem. If you balance the equation and you still only have one hydronium, then you're probably good. But we only lose one proton, and that leaves a hydrogen sulfate ion. That's one of your polyatomics. Now, this can dissociate also, right? It can go like water, and then it can produce SO4 2 minus plus another hydronium. Right? So the dissociation of protons from an acid are stepwise, one proton at a time. So let's take that information and answer this question. So what's the acid-base pair? Well, there's your acid, and there's your base pair. So let's see, HF and F minus right there. Okay? Okay. There's a characteristic that's particular. Well, it's not only possessed by water. There are a number of substances that can do this. But water is the one we focus on now because it's the solvent. And we need to understand that water can be both an acid and a base by the Bronsted-Lowry definition. Water can donate a proton or it can accept a proton. Okay. And this is called amphoteric behavior or amphiprotic. Both of them, well, they're slightly different words, but they describe the same phenomenon. Amphi means both, which means water can be both an acid and a base under different circumstances. Let's see. Hold that thought. We're going to work on it a little more in a minute or two. Yeah, we're going to get there. Just remember that water can be either an acid or a base. So if you put a base in solution, the water acts like an acid, like ammonia. It donates the proton. Or if you put hydrochloric acid in solution, water acts as a base. It can accept the proton. So acids come in basically three flavors: monoprotic, diprotic, triprotic, for our purposes. So that means they have either one proton per molecule that can dissociate, or they have two that can dissociate, or they might have three that can dissociate. Now, there are probably instances where you can have more protons that can dissociate. Those molecules will be a bit complex for our work in here. So we're gonna stick with mono, di, and triprotic, and begin by talking about only inorganic acids. You can have organic acids too, but we're going to focus on inorganics. And the di and the triprotics fall under the general category of polyprotic. Right? They have two or more protons that transferred during an acid-base reaction. Okay, now our definition of strong. What does strong mean? The intuition that accompanies a student into a chemistry class is that a strong acid is one that will damage your skin if you spill it. Okay? So if you dump a bottle of vinegar on your skin, no big deal, unless you have a cut. Then you find every cut on your arm. But it doesn't damage your skin. We consider that weak acid. But if you take a bottle of muriatic acid, you can buy it at the feed and seed store, and use it to etch concrete before you seal it, which I've done before. It's not a fun job, but it works. It opens up the pores of the concrete and cleans them of any accumulated products of some reaction. But it cleans the surface, gets it ready. Muriatic acid, and it's concentrated. So if you pour that on your skin, oh yeah, you'll start eating right away. Now that's what we normally think of as weak and strong. But that vinegar is only 5% acetic acid. When I worked in research, we kept in our stock 100% acetic acid. This is called glacial. Now, what's the difference? The difference doesn't have anything to do with the molecule. It's the same molecule, right? And that's what we're talking about in chemistry. When we say strong acid, we're talking about the nature of the molecule, the identity of that molecule. It's still a weak acid, both places. But I guarantee if you dump this on your arm, it will burn. Whereas that one won't. Okay, so the difference is the concentration, not the nature of the acid. So when we say strong acid, we need a better definition. Okay? So a strong acid is one in which the protons are very close to 100% dissociated. In other words, when you put hydrochloric acid in solution, it reacts with water and it makes hydronium plus chloride. Right? Now, for all intents and purposes, I mean, we can write. We can do that. But for all intents and purposes, strong acids do only this. They only go that way, and there's nothing left over here. Okay, that by chemical definition is a strong acid. A weak acid, by contrast, is this molecule reacting with water to produce C2H3O2 plus hydronium. Okay, now this one is in equilibrium. All right, go both ways, but most of it is here. Just a little bit of it is over here. So as you increase the concentration, you naturally get more of this over here. I mean, it doesn't happen in a linear fashion. In other words, if you go 50%, that doesn't mean that you have 10 times as much of this over here. In fact, it's less than 10 times. But if you get 100%, then, well, there's no water for it to react with, right? So it has to react with itself, which it does, which is another topic altogether. But the equilibrium position of a strong acid is way, way far to the right. For all intents and purposes, 100%. Right? And these are strong acids. Hydrochloric acid, hydrobromic, hydriodic. Notice any trend there? Halogen, halogen, halogen. Which one's missing? Hydrofluoric acid. Hydrofluoric acid is considered a weak acid. And there are reasons for that. Which we may cover, we may not. I'm not sure if I've got that in this lecture. Maybe beyond the scope of this course. Nitric acid, these other polyatomic ion acids, Nitric, chloric acid, perchloric acid, it's extremely strong. Sulfuric acid, we'll talk about this in a minute, I hope. Sulfuric acid is strong for the first proton. Second proton, it's a weak acid. So HSO4 minus is the weak acid. But the strong acid is sulfuric acid because this first proton goes 100%. And I'll add that to the bottom of the slide. Polyprotic, that's characteristic of all polyprotics. If it's a strong acid, it's only strong for the first proton. Okay, so weak acids, they still have that reaction with water, but their equilibrium place is shifted far to the left, as written, right? Undissociated acid. This is your artist's idea of strong acid versus weak acid, and it's a valid approach, right? You get this acid, and it produces molar equivalents of hydronium and conjugate base. Right? So if you have 1 mole of this, you're going to have 1 mole of hydronium and 1 mole of conjugate base. Whereas with a weak acid, you still got mostly undissociated and a little bit of conjugate acid and conjugate base. Those were acids. Strong bases. Generally, strong bases are derived from, and these are Arrhenius bases, notice. They've all got hydroxyls. Okay. The first group, alkali metals, form strong bases with the hydroxide. Lithium, sodium, potassium, rubidium, cesium. They're all strong bases. The group 2s, the alkaline earths, they only become strong at calcium. Calcium, strontium, barium. Magnesium is a weak base, and beryllium hydroxide would be a weak base. The problem is that there's a solubility issue. So you don't get 100%, you don't get high solubility. In other words, you put a gram of calcium hydroxide in water, all of it doesn't go into solution. But by definition, whatever goes into solution dissociates into calcium and hydroxide ions. Okay? Let's see. All right. So which one of these would represent a strong acid in solution? Right, there's our generic acid, HA. What you would want is to have the correct conjugate acid, conjugate base pair, acid, base pair, base, acid. And you would want to know something about the equilibrium. The equilibrium is shift far to the right. So it looks like B would be the best answer there. Okay. When we talk about equilibrium, and I'm pretty sure we covered that ground a little earlier, writing equilibrium constants. But for weak acids, in this case, we're just talking about acids. Well, strong acids, everything's all on the right-hand side. So an equilibrium expression has little meaning. But for weak acids, then you get some on the product side and some on the reactant side. Right? So we can use the law of mass action to write an expression for that dissociation. Actually, this is, excuse me, I'm using the wrong term, that ionization. So when we, I don't even have to draw this one up there. So when we have our acid reacting with water, producing hydronium and conjugate base, the law of mass action says the concentration of hydronium times the concentration of conjugate base in the numerator, then divided by the reactants, right? HA aqueous goes in here. Why don't we put water? Because water is a pure liquid. And remember, pure liquids and solids don't count. Only solutions and gases count in this expression. And we give that a little subscript A for, this is the equilibrium constant for acid ionization in water. Now sometimes, I will write this up, sometimes for convenience, once we know that this is aqueous, sometimes it's more convenient just to write it as an ionization like this. And these are aqueous and aqueous. You have to understand, though, that this is an abbreviated form. Those protons never exist alone in solution. They're always attached to something. Like a free-floating proton is like, you know, it's a target for any other molecule, and they never survive alone. They're always transferred from one place to another. But the expression here, this abbreviated version, is just as valid for this expression as the correct version, right? If we change this to hydrogen ion instead, just leave the water out, then we still get the same value right here, exactly the same. And it would just look like this. Okay? And another thing you may notice in the law of mass action, for some reactions, not acid-base, but some reactions, you have powers here, like coefficients become the powers. Right? In acid-base reaction, because of our definition, you don't have powers there. It's just one, right? Because with one dissociation, you've only got one here and one there, coming from one here. Okay? So these will always be exponents of 1. Okay, there's another concept. It's called percent dissociation. In fact, this sort of defies the definition, doesn't it? Right? We said acids ionize. They don't dissociate. But we're kind of stuck with it because the scientific community has chosen this description as dissociation, perhaps because you can apply the same concept to bases. So they just say, we're going to call them all dissociation, when we realize that it's ionization for acids and dissociation for bases. But actually, it's not always. With a Bronsted-Lowry definition, the transfer of a proton could be an ionization. For instance, if one is being transferred from water to ammonia, that's definitely a dissociation. It's not ionization. So perhaps we should settle on dissociation as covering all the bases. Okay, so if we start with this equation, and then we want a definition for how much of that acid actually dissociates. All right, so you take the concentration of A minus, the conjugate base, and divide it by the acid from which it was derived, times 100. And that's percent dissociation. So if we say hydrochloric acid is 100% dissociated, right? That really has no meaning with this definition, but for an example, all of it ends up over here, which means there's nothing over here, right? And mathematically speaking, if HA is 0, what does percent dissociation mean then? It means infinity. Anything divided by 0 is infinity. So if you have just a little bit here, so it's kind of a misnomer for strong acids. Percent dissociation is only valuable when we're discussing weak acids or weak bases. All right. So, so it looks to me like they're mixing terms. Degree of ionization and then percent dissociation is the calculation. All right, so as an acid, acid strength increases along with an increase in percent ionization or percent dissociation. So if you get a bigger number over here, then you can say something about the strength of the acid. But it's not absolute, because this value will vary depending on the actual concentrations of the conjugate base and the acid that's left over. Right? This varies. It's kind of like the difference between equilibrium constant and equilibrium position. They're related, but they're not the same. The equilibrium constant is just that. It is a constant. As long as the temperature doesn't change, this value will be constant. So you can change these values all you want. As long as you're at equilibrium, they will give you that same value, constant. Whereas if you change concentrations, if you move the position of the equilibrium, then you end up with a different percent dissociation. Or in equilibrium terms, you have changed the equilibrium position. Okay. So the more definitive definition of acid strength has to do with Ka. Right? Bigger Ka means a larger numerator, right? Smaller denominator. So a larger Ka means a stronger acid. Okay. So you can do a similar calculation for bases. And here we have the base, and it's going to accept a proton from water and give you this conjugate acid. Now it has a proton it can donate, and then the hydroxyl, which is the conjugate base of water. Okay, the expression for Kb then is this BH plus times this OH minus divided by this B, and we leave the water out. So you get a value for the base ionization constant, or the equilibrium constant for the base in water. Now the tendency is one of the common mistakes that students make, and when you first learn about these Ka and Kb comparison, is to say, oh, Kb is just the inverse of Ka. Well, that would be a fatal mistake, an error. They're not the same. We can relate them, but they're not the same by mathematical means in terms of inverting one to get the other, right? Because acid has no hydroxyl in its expression. It's got the conjugate base is A minus, right? And then you have an acid down here. It's just not possible. All right, so those are acids, bases. Let's define our salt before we move on. Let's see. Okay, so we've defined acid, base, Bronsted-Lowry terms, proton donor, proton acceptor. We've defined strength of an acid or a base based upon percent dissociation or equilibrium constant. Now we want to define a salt in chemical terms. A salt in chemical terms, simply put, is you react an acid and a base. And the easiest way to explain this is use the Arrhenius version. So we have an acid and a base. So what do? Well, this proton goes over here and makes water. Oops, makes water. And this A minus combines with this B plus to make, right? There's your salt, and there's your water. So an acid reacting with a base produces a salt in water. It gets a little more complicated with bases that don't have hydroxyls. But for most cases, you produce this salt from an acid and a base. That is a chemical definition of a salt. Now, that salt may be soluble. Most of them are. Right? Most of them are soluble, which means you have independent ions in solution. But occasionally, you get an interaction of a B and an A that produces an insoluble salt. And then you need that chart that I'm sure I've given it to you somewhere. Maybe it was in the last chapter. Where you look to see, is it soluble? Sodium chloride is soluble to a large degree in water. Some salts, if we reacted well, nothing comes to mind right now, but that's neither here nor there. So the chemist's definition is the reaction of an acid and a base in which the cation from one combines with the anion of the other, and that makes a salt. Examples, right? Potassium chloride, it's completely soluble. Potassium sulfate would be a salt out of this reaction. But notice, this reaction covers both protons. Right? So it actually goes through steps. In other words, you dissociate one hydrogen ion, and it attaches, the hydrogen sulfate ion attaches to the potassium. But then you get a secondary reaction, which takes it to completion. Okay. And this is called a neutralization reaction. Now, why do we say neutralization? It's a neutral position. If you don't have excess acid or excess base, then your solution is neutral. And not all chemical reactions, acid-base reactions, give you a neutral solution. And we have to define that, of course, in just a minute. But as a general term, we are trying to neutralize an acid with a base, or a base with an acid. So that's where it comes from. All right. Now, here's one for you. If you have pure water will undergo acid-base reaction. Remember we said water is amphoteric or amphiprotic, can go both ways. Well, if it's just pure water, then it does. One molecule might act as an acid and the other act as a base. That's what we see here. This proton is being donated. Well, actually, that's going backwards. I would have put it this way. We got water, and this is pure liquid. This is pure liquid. And now we have hydronium plus hydroxyl, aqueous solution. Okay, so what happened? Well, let's see, if we keep them in order, one proton here transferred there. And that makes the hydronium. So this is the proton acceptor, and this is the proton donor. So that makes this the conjugate acid, and this makes that the conjugate base. Okay. Now, why are we going to all this trouble? Because that reaction is real. It happens. In aqueous solution, this reaction is always there. No matter what else you do to it, it's there. And it must be obeyed. No matter what you put in that water, this reaction has to be present and obeyed. If we were to write an acid dissociation constant for this, we would say Ka equals what? Hydronium times hydroxyl. Well, those are both liquids, right? So nothing goes in the denominator. It's just that one times that one, because those are pure liquids. Right? We give this a special name, Kw, for water. So this would be, and I'm going to abbreviate it now. Sometimes it's written this way. Just like before, it's just easier to deal with that rather than this big thing here. Okay, so that would be, the reaction I wrote up here was this one in reverse. All right. Oh, I see what they were getting at. This is the reaction that occurs when you neutralize. This is a neutralization reaction, and this is the formation of water along with the salt. This is the self-ionization of water that I described here. Since water is amphoteric, can behave as either an acid or base, then it does. Now, most of the equilibrium is this way. It prefers that. Okay? And there's a value for this at 25 degrees Celsius. This value is going to be 10 to the minus 14. It's a very small number, which means the equilibrium position is way over here. You just produce a few of those. Now, how did we get this value? Well, if 1 mole of this and 1 mole of that react, then they're going to give you 1 mole of that and 1 mole of that, correct? So if we know the concentration of one, we know the concentration of the other, which means that one is equal to that one in pure water. So what would it be? 10 to the minus 7 and 10 to the minus 7, correct? It's just the square root of 10 to the minus 14. So minus 7, you add the exponents, and you get minus 14. So this is a neutral solution. 10 to the minus 7th concentration of hydrogen ions and 10 to the minus 7th concentration of hydroxyls. That's a neutral solution. I left out the 1 because, you know, it's understood. Now, no matter what we do to the solution, this expression always has to be the same. Now, these values might change. Right? Let's say we increase the amount of hydrogen ions, say 10-fold. So what's 10 times bigger than 10 to the minus 7? 10 to the minus 6, correct? Now, what does that mean this one has to be? 10 to the minus 8 to give you 10 to the minus 14. So this always has to be obeyed, no matter what you put in it. Acid, base, whatever. Salts. Okay, and that's a good thing. Because whatever we put in there, if we can measure one, if we know something about the acid or base we put in there, then we can calculate what's left over. Because these terms always are in equilibrium. Okay. So the balance is if the hydroniums equal the hydroxyls, you have a neutral solution. If the hydroniums exceed the hydroxyls, you have an acidic solution. And if the hydroxyls exceed the hydroniums, you have a basic solution. And you can measure that in a number of ways. You can actually perform a titration and determine what the actual concentration of each of these is in solution. Or you can get a semi-quantitative measure by using little strips of paper that have a dye in them, and they turn different colors depending on the concentration of acid or a base. Or you can use an electronic meter that is a probe, goes into the solution and measures conductivity, basically, at the probe, and interprets that as concentration. Okay, so there we are. We just say what we showed on the previous slide. Acids are weighted toward hydroniums, bases are weighted toward hydroxyls. And if they're equal, you have a neutral solution. Okay, so let's work a problem or two. All right. So if we have, let's see, calculate hydronium or hydroxyl as required for each of the following solutions, and state whether the solution is neutral, acid, or basic. Okay, remember, if we're going to say acid, base, or neutral, we have to find out what the hydronium or the hydrogen ion concentration is. Right? It's a balance. We have to compare. So if A says that the hydroxyl ion concentration is 1 times 10 to the minus 4 molar, right? Then we need to find out what this one is, right? So we have an equation for that, right? Kw equals 10 to the minus 14, which is equal to this concentration. I'm going to abbreviate again. I'm just going to use hydrogen ions. And then this concentration, which we can drop the 1, 10 to the minus 4. So now we have an equation in one unknown. It's solvable. So we just say this one is equal to that one divided by this one. 10 to the minus 14 divided by 10 to the minus 4. So if we bring this into the numerator, it becomes positive. Now we have 10 to the minus 10 molar for hydrogen ions. Okay, which one's bigger? 10 to the minus 4 is bigger than 10 to the minus 10. So this is a basic solution. Okay? How about the next one? Well, let's be consistent. There we go. We're starting off with 2 molar of acid. Okay? So we can do the same type of calculation. We can say 10 to the minus 14 is equal to 2 times hydroxyl. Okay? So hydroxyl will be this one divided by 2. Which is equal to, actually 1/2 times 10 to the minus 14, which is 0.5, which is 5 times 10 to the minus 15. Okay? Or you could just make the direct comparison. 2 is much, much greater than 10 to the minus 7, right? Remember, neutral would be 10 to the minus 7 for both hydrogen ions and hydroxyls, because multiplying them together, you get 10 to the minus 14. So 2 is much, much bigger than 10 to the minus 7, which makes it acidic. I was comparing this one to that one, which is also valid, but this is quicker. Okay, an aqueous solution in which the concentration of hydronium ion is higher than hydroxyl is, by definition, an acidic solution. Now, scientific notation is useful, but it was still too unwieldy for this one particular scientist, Sorensen, a Danish scientist in the early 20th century. He says he was working with living systems too, and most biologists are kind of lazy. I can say that because my original training was biology. But Sorensen wanted a way to compare solutions in a more concise way. He wanted smaller numbers. He didn't want the scientific notation, just wasn't good enough. So he applied a log transformation. And that's all it is. It's a mathematical transformation of the hydrogen ion concentration to produce a new value. Well, notice what you get. Let's start with neutral hydrogen ions, 10 to the minus 7. Okay? What happens if you take the log of that? And this is common log, base 10. Okay? So what's the log of that? Well, the log of that expression is the power of 10. So we have minus 7, right? That's the log of 10 to the minus 7. Power of 10 equals that value. But Sorensen didn't want negative numbers either. Right? He wanted all positive numbers. So he said, all right, I'm going to put a positive out here. That makes this one positive. And he called this little p, big H. Small p, capital H. If you write capital P, capital H, it's wrong. If you write small p, small h, it's wrong. Hello? Okay, so that's Sorensen's contribution to acid-base chemistry, the pH. But it's a mathematical transformation. In other words, if you have a concentration in here, you can do the same thing to any, right? We could do it to hydroxyls. Let's say hydroxyls were in here, right? Do the same calculation, but it's not pH anymore. It's pOH. Okay? You can even do it to equilibrium constants. So if you have a K for your acid, so what would that be? It would be pKa. Okay? It's just math and definition. All right. So notice what would happen if we went to a higher concentration of hydrogen ions. 10 to the minus 6 instead. What would that value be? 6 pH. Okay, so what does that mean for interpreting pH values? The higher the concentration of hydrogen ions, the lower the value. Right? pH 6 is more acid than pH 7. So it goes 7, 6, 5, 4, 3, 2, 1. Gets stronger and stronger, not stronger, gets more acid, more hydrogen ion concentration. And if it goes past 7, if it goes 8, right, if you made that 8, now you're into the base region. 8, 9, 10, 11, 12, that's basic solution, pH. All right. So let's calculate the pH for these two guys. This one's easy. Negative log of 1 times 10 to the minus 4 hydrogen ion concentration, right? This is hydrogen ions. So the negative log of that, since that's 1, we can ignore it. Well, actually, I want to make a point here. How would you interpret the log of a product? The log rules say that the log of a product is the same as the log of this one plus the log of that one. Right? That's how you interpret logarithms. This minus becomes a plus when you split them apart. So what's the log of 1? 10 to the 0 power is 1. So that's 0. And then you have a negative times a negative 4, which equals 4. So the pH of A is 4. All right? All right, what's the pH of this one? Well, we can go about this 2 different ways. We're going to do it the hard way first. 0.040 hydroxyl. We know that Ka in solution is always 10 to the minus 14. And that's equal to hydrogen ion times hydroxyls. This is our unknown. And this is the one we know, 0.040 molar. All right, so all we have to do is divide this one by that one. Let's see, that would be 4 times 10 to the minus 2. 10 to the minus 2, which is equal to 1/4 times 10 to the minus 12. Right? This becomes a plus, reduces, actually increases that one to minus 12. And then this is 1/4. So now we have 0.25 times 10 to the minus 12, or 2.5 times 10 to the minus 13 molar. So that's the molar concentration of hydrogen. Now we need to do the log transformation. Negative log of that value. I need my calculator for this one. I can't do logs in my head. 2.5 and then exponent minus 13, and then take the log. And change the sign. So that's 12.6. pH 12.6. Okay? There you go. That's the long way, the hard way. Believe me, there's an easier way. Hold on a second. Let me catch up with my hard copy. Let's see. Okay, we'll get to it in a minute. Next, what if you determine the pH of a solution to be some number? Now you want to find out what is the hydrogen ion concentration. Purely mathematical. It's the definition of logarithms. All right? So, by definition, when you say the log base 10 of x equals y, what's the other interpretation of that? It's 10 to the y power equals x. So if we say the log of some number is 5.85, then x is equal to 10 to that power. Okay? pH calculation introduces another fly in the ointment, the negative sign. Okay? So we have to put this negative over here first before we can break that log apart. So this becomes log of x equals negative 5.85. So now 10 to the minus 5.85 equals x. And x is our hydrogen ion concentration. So you just need to learn how to use your calculator to do that. So you just need to find out. Your calculator has, usually it's close to the log key. So if you have a log button, then you hit the function key, and 10 to the x should be right above it. Most calculators, they are. So I should say 5.85, change the sign, now it's negative. And then I hit the 10 to the x key, and it gives me 1.4 times 10 to the minus 6. Okay? Now, why did I only put 2 significant figures here when that has 3? It's the nature of logarithms. When you interpret logarithms in terms of significant figures, the number of decimal places determines the number of significant figures in your answer when you're going backwards. So if I were going this direction and I work from that one, then significant figures just 2 here, I can have 2 decimal places here. It's just the nature of logarithms, and we don't have time to go into the mathematical details here. Okay, so there you go, and there you go. That's molar, by the way. All right, so pH range. If we start with 7 as neutral, then anything greater than 7 is basic, and anything less than 7 is acidic. Now, what's the practical range? The practical range of pHs, since Sorensen was interested in living systems, he wasn't interested in pHs that were much below 2. Might go to 1 on a stretch, or anything greater than 12. Living systems don't react kindly to those high or low pHs. But mathematically speaking, you can calculate the pH of any hydrogen ion concentration, no matter how strong or how weak. Right? That's just math. but these are practical. Right? Stomach acid, these are vegetables and there's eggs, butter, things. So most of those pHs occur in this narrow range. Stomach acid is anywhere between 1 and 2 pH. That's hydrochloric acid. Okay, just to check, there's your correct mathematical expression for pH. And we sometimes substitute hydrogen ions there instead of hydronium. So that works also. Okay. So if I mentioned this earlier, you can calculate, this mathematical expression can be used to calculate pOH or even pKa. Right? pKw is a special pK term for water. Right? So if you take the negative log of this value, you get 14. Correct? Well, notice that if we take if we say Kw equals that and that, then if we take a negative log of that entire expression, we just take the negative log of this, negative log of that, negative log of that. Remember, if we take the negative log of this product, then it becomes addition, summation. So pKw here equals pH plus pOH. Okay. This is 14, always 14. Then that's equal to these two terms. So now, if you're given hydroxyl concentration, then all you have to do is calculate pOH and subtract it from 14, and you get pH. So that was the quick, easy way that I was talking about earlier. We did it the hard way first. Now this is the easy way. So for this problem, we're given the pKa for hydrogen fluoride, hydrofluoric acid in aqueous solution. Right? Which is, and the, oh, well, this just asks you to calculate the pKa. So negative log of 6.8 times 10 to the minus 4 is equal to what? Just plug it in. 6.8 exponent 4, change sign, and then take the log of that. And change the sign again. So that's two significant figures, 3.17. If this is the Ka, wait a minute, this is the Ka, and this is the pKa. 3.17. Now, what value is the pK value? Well, notice the K for a weak acid puts, let's use this one as our example. Right? So the expression of K for that acid would be hydrogen ions times fluoride divided by HF. Right? So, if the concentration of acid gets bigger, then the negative log expression would get smaller, just like calculating pH. So the smaller, the smaller the pKa, the stronger the acid. So now you can compare pK values among acids and find out which one is the stronger in chemical terms. Okay. Let's see. Yeah, they rounded it off. Close enough. 3.17. Oh, wait a minute. I'm sorry. 6.3. That's a different calculation. So 6.3, yeah, would give you 3.2. So let's compare 3.2 versus 3.17. Which one is the stronger acid in chemical terms? This one. Not by much, you know, by 300ths. But remember, we're in logarithmic terms, right? And logarithms, common logarithms, go up for every 1 unit change in logarithm, you get a 10-fold increase in the number from which it was derived. That's why pH 6 is equal to 10 times the strength of pH 7. When you change 1 unit, you've actually increased the hydrogen ion concentration 10 times. All right. So let's talk about salts again. They are ionic compounds, right? They're composed of the cation and the anion from, theoretically, an acid-base reaction. Now you can have salts, right? Just pure salt in a container. You don't have to conduct the acid-base reaction to get it. But by definition, we're saying that's how it's derived. These salts break up into individual ions in solution, but there's a special way that they do it. And it's called a process of hydrolysis. When you react salt with water, you get a combination of hydronium ions and hydroxyl ions, hydroxide ions, both of them in solution. Now, depending on the salt, you may get more of the hydronium than the hydroxide, or vice versa, more hydroxide than hydronium, in which case the pH of the solution could be acidic or it could be basic. Okay, so how do we know? Well, let's go with rules of thumb first. When you create a salt from a strong acid and a strong base to neutrality, then the salt that results from it is like equal armies, right? They're thick, they butt heads, and nobody wins. You're neutral. When you combine sodium hydroxide and hydrochloric acid, you get sodium chloride, which is considered a neutral salt. When you dissolve that in solution, then neither sodium nor chloride react with water to produce the original acid or base. Correct? Look what happens. If you get sodium chloride in solution, you just put the sodium chloride in now, not the acid base, but the sodium chloride. Then the sodium chloride breaks apart into sodium and chlorine. Okay? So what could they potentially do? Well, the sodium could react with water, theoretically. And it would react with the hydroxyl to produce this. Okay, is that possible? This is a strong base. It prefers to be in this form and the hydroxyl form. That reaction will not occur. Similarly, we could say this plus that. But that's a strong acid. It wants to be like this. Well, and that. That one will not occur. So when you put sodium chloride in solution, it has no effect on the hydrogen or hydroxyl concentration. They're still 10 to the minus 7. Any strong acid, strong base reaction will give you that result, a neutral solution. That's the easy one. If you recognize this as derived from a strong base and this is derived from a strong acid, then you can say the solution will be neutral when you dissolve that salt in water. So what are the other possibilities? Well, we could have, we could have a strong acid and a weak base as our source. Right? So ammonium hydroxide plus hydrochloric acid, weak base, strong acid. That produces ammonium chloride in solution. The rule of thumb is derived from weak base, strong acid, dissolve that salt in solution, you get an acidic solution. And here's the explanation. What two ions do you have in solution? We have chloride and you have ammonium. Chloride, we already showed, won't react with water. But ammonium prefers to be ammonia in solution. So it's going to give up that proton readily to water molecules and produce ammonia and hydronium. So there's your acid. In fact, if we use the rule of thumb, the tendency would be to say, oh, there's a strong acid, that makes it acid. Well, rule of thumb is okay, but the reason, the chemistry behind it, revolves around the base. The NH4 reacts here with water. It wants to be ammonia and produces the hydronium. And of course, well, no, that's the long and the short of it right there. What if it's the other way around? Have a weak acid and a strong base. Well, based on our rule of thumb, it should be a basic solution, correct? Okay. If these are the base and acid reactants that produce the salt, then we see that sodium hydroxide would be a strong base and acetic acid would be a weak acid. So we should have a basic solution. But again, it's not because of the strong base, it's because of the weak acid. The strong base, the sodium, is not going to react with water. It wants to be sodium only. The acetate ion reacts with water. It prefers to be acetic acid, right? Because it's a weak acid, it wants to hang on to that proton. That's what weak acid means. This is my proton, you can't have it. So what it does is it takes a proton from water and leaves hydroxyl. There's your base. So the basic solution is formed from the weak acid conjugate base. This is the conjugate base of acetic acid. Okay. Now, what if you have a weak acid and a weak base? There it's problematic. It's solvable, but what you have to do is compare the K values for the weak acid and the weak base to see which one wins. And this course, really, we don't have time or the need to dig into that one in detail. But these are examples of weak acid, weak base, right? There's the derivation from a weak base, and there's the derivation from a weak acid. So, and in this case, actually, the K values for each one of these are almost identical. So this would be a neutral solution. That's a possibility with a weak acid, weak base. But for this one, you have nitrous acid versus ammonium hydroxide as the source. And in that case, you would have to decide which one wins. Right? And we're not going to go into that here. Just be aware of the fact that that's one problem that needs a little more work. Okay, some salts hydrolyze when placed in water. The salt dissociates in water to produce hydronium hydroxide or both. When the salts of the strong acid and the strong base are placed in water, you get a neutral solution. Okay, that's the easy one. Now, what's a buffer? A buffer in chemical terms is a solution that resists change in pH when acid or base is added to it. So if we have a buffer solution, we add acid to it, it might shift a little tiny bit toward acid, but not as much as you would expect. And conversely for base. So that's why we say it just resists the movement in pH. Now, you can add enough acid to a buffered solution that it will exceed its capacity, and then once you go past that capacity, then it just goes acid quick, fast, and in a hurry. Most buffers are composed of a weak acid and its conjugate base. So we would need, for this one, right, acetic acid and its conjugate base. Those would both have to be in solution in the proper ratio. Right? We're not just forming it from the acid. We're actually adding extra acetate to the solution so that you get a proper balance. And in fact, the ideal balance between them is actually that, equal concentrations. That gives you the best buffer for a weak acid. It doesn't matter what the acid is. 1-to-1 ratio. So these two species are in solution, and we can look at it in terms of weak acid dissociation. So let's say C2H3O2 yields that one plus this one. Like that. And we have so much of this and so much of that. Let's just say, for argument's sake, we have 10th molar here and 10th molar here. Okay. Well, in the first place, how do you do that? Right? How do you get these two equal? Up to this point, we just added acid, and right, and most of it's over here. There's not enough over there. You add this as the salt. The sodium salt would be a good choice. So sodium acetate and acetic acid in equal molar amounts would give you that situation. And the sodium is a spectator. We've already established that sodium doesn't react with, well, it definitely doesn't react with that because you put it in a solution and it completely dissociates. But it doesn't react with water either, so sodium is a spectator. That's why we can focus on this reaction. Okay. So the buffer has two components to it. It has the acid and the conjugate base. Now what happens when you add acid? Remember Le Chatelier's principle. If this is at equilibrium, if we disturb it, the system will react to mitigate the disturbance. So if our disturbance is to add this, what's it going to do? It's going to shift back this way. It's going to produce that and consume most of that. But now we have slightly higher concentration of hydrogen ions, but nowhere near as much if there were no reaction for it to undergo. All right, so we've consumed hydrogen ions if we add an acid to this buffer. What if you add the hydroxyl? Okay. If you add hydroxyls to it, if you add a base, it's going to react with those hydrogens and make water. Remember, the equilibrium for water dissociation is way, way towards water. So this reaction will occur fast, and it will get done toward water. So when you do that, you're removing hydrogen ions, correct? So Le Chatelier says you're going to get a shift that way. So now this produces more hydrogen ions to replace those that were lost. It won't replace all of them, but it will replace most of them. So that's how the pH is stabilized, whether you add acid or base. And this is an explanation in slide form for everything that I just said. Okay. What two active species? A substance that resists change in pH. Okay, that's the definition of the buffer. A substance that resists pH when small amounts of acid. Oh, okay, both of them. A and B are both. And C, a weak acid and a conjugate base. Now, it is possible to make a buffer with a weak base and its conjugate acid. Right? But the reasoning, the logic is the same. It just depends on where you want to establish the buffered pH. Do you want the buffered pH at a low pH, middle, high pH? If you choose your components, your acid-base components that go into the buffer, you can tailor that buffer pH. I'm not so sure we're going to be able to do it in this class. Takes a little extra work. But at least you know the basics of buffer behavior. Now, this equation is extremely valuable. It was developed first by Henderson, and, well, Henderson gave it the initial push, and Hasselbalch came along and extended it. So that's why they were hyphenated name, Henderson-Hasselbalch. If you start off with the dissociation of an acid here, right, and write the expression for its K value, right, products divided by reactants, and then you solve for the hydrogen ion concentration. It's just mathematical, right? Just move these two over to the other side, and when you do, you have to flip them, right? Now this one is in the numerator, and that one's in the denominator, times Ka. Now what are we going to do? You may have already guessed. We're gonna bring Sorensen on board. pH. We're actually going to do the log transformation that gives us pH for this side, pKa for that side. Okay, So negative log of that, negative log of that, negative log of this. And notice when you take the log of a product, you get a summation. Right? There's negative log, negative log. So now we have this is pH, this is pKa, and we're going to leave this one alone because there's really no good expression for pHa over A minus. In fact, we want to keep them separate because the ratio here between these two is the important term in this whole equation. All right, but Hasselbalch said, I don't like negatives, right, unless I have to. So we're going to get rid of that negative. So how do you get rid of a negative in a log term? Well, if you make that a positive, then you flip this term. It's A minus over HA. Okay, now you got your positive, and you got the conjugate base divided by the acid. Plus, we'll take the log of it first, and then plus the pKa, and that will give you the pH. And remember these square brackets. Those are equilibrium concentrations. So, for a particular buffer, we establish a buffer, say, with acetic acid and its conjugate base. As long as this ratio doesn't change, then the pH will always be that buffer pH. Because that ratio, you just take the log of the ratio, and if the ratio is the same, you get the same log. So we could have 10th molar here and a 10th molar there, or we could have 1 molar here and 1 molar there, or we get a 100th molar and 100th molar. You still get the same ratio. That's the important thing for buffered solution. Now, if these two solutions are equal concentration, what value do you get? Well, if this is equal, say this is 10th molar and this is 10th molar, what do you get? 1. And what's the log of 1? 0. So if you get equal amounts here, you get this term as 0. That means the pH is equal to the pKa. So the pH of your buffered solution is dependent upon the pKa, and the best place for it is where this whole term is 0. Now, let me see if I do any explanation here for that. Well, we're about to run out of time, so I'm going to have to let that explanation go. I was going to show you a titration curve, but we don't have time for it. Okay, what's the pH of a buffer solution that is 0.45 molar acetic acid and 0.85 molar sodium acetate? Okay, so there's your conjugate base delivered into solution as sodium acetate. The Ka for the acetic acid is 1.8 times 10 to the minus 5. We'll use Henderson-Hasselbalch. Right? So what is the pH? Well, the pKa would be the negative log of 1.8 times 10 to the minus 5th plus the log of conjugate base 0.85 divided by the acid 0.45. Okay? So now it's just a math problem. We'll take that ratio and do the log. 0.85, 0.45 divided, and then take the log of it. And then we'll take the negative log of this value. 1.8 times 10 to the minus 5. And take the log of that and change the sign. And then add those two together. And I get 5.02 pH. That's the pH of this buffer. Now notice, it's not that perfect ratio that I mentioned earlier, 1:1. So you can make buffers at different pHs. It's just that if you make them 1:1 ratio, then you're right in the middle of the buffer range. And it will respond equally well to either adding acid or base. If you're at a different end of the buffer range, then it may not be able to accommodate as much base as it does acid. And it depends on your purpose. I mean, do you want the buffer, do you expect the buffer to have to handle acid more than base? Then you take that into account when you're preparing your buffer, and vice versa. Right? So there's the equation. I just substituted values in there. 5.02. Okay. Mathematical expression for Henderson-Hasselbalch is A and B. Now, if this one had a negative sign right there, it would be valid also, but it doesn't. Got a positive, and you can't have them that way. So A and B are the only right ones for this one. Okay, what's an electrolyte? Electrolyte, by definition, is any acid, base, or salt, when it's in solution, will conduct electricity. You may not know this, but pure distilled water is an insulator. If you have a low voltage source that you put into water, so you have an electrode here, and you have, say, a light bulb here, and you have a source, a voltage source here, right? Now, how does electricity work? It needs a circuit. It has to go in a circle. It has to go all the way around. So, if these two electrodes are not touching, then it depends on whether or not there's something in that water to transfer the charge from one electrode to the other. Water does not dissociate well. We know already 10 to the minus 14 to make hydrogen ions and hydroxyls, right? That's not enough. So water is an insulator, electrical insulator. But if we put an electrolyte in there like hydrochloric acid, that makes hydrogen ions and chloride ions, and you get a transfer. You complete the circuit, and now your bulb lights up. That is, by definition, an electrolyte. When you get your medical reports back from blood work and urinalysis and so forth, they report electrolytes. The electrolytes on that report are all ions, right? They'll report sodium, right? If you like salt on your food, your sodium levels are probably going to be high. They even report chloride. They report potassium. They report calcium and magnesium and several other ions. But those are all your electrolytes. In solution, they conduct electricity. Okay. So a non-electrolyte won't conduct electricity. Here's your example. Sucrose, table sugar, or glucose, blood sugar, won't conduct electricity. It does not ionize. It's very soluble in water, yeah, but it doesn't make ions. Whereas if you put an acid, a base, or a soluble salt in there, then you're going to get that light bulb lit up. Now, the difference between strong electrolytes and weak electrolytes is the strength of the signal, right? How strong is the light bulb? And that's based upon whether or not you have more ions in solution with a strong than you do with the weak. So strong acids, strong bases, and soluble salts will be strong electrolytes. But weak acids and bases will be weak electrolytes because they do not dissociate sufficiently to produce enough ions to conduct the current. All right. So now here's a concept called the equivalent. Whoops. Fumble fingers. Abbreviated EQ. Now, why would we want to invent another term? Well, scientists don't do that unless it's helpful. And the use of the equivalent is particularly valuable when we're talking about acid-base reactions. It's an expression of the concentration of ions derived from their source. Here's the definition. It's the number of moles of an ion needed to supply 1 mole of positive or negative charge. So 1 mole of sulfate ion actually equals 2 equivalents. Why is that? Well, let's use a simpler one first. 1 mole of chloride ions equals 1 equivalent of chloride. The reason for that is that will produce 1 proton, maximum. Right? But if we go to sulfuric acid, if we extract both protons, then you get 2 protons and a sulfate. That's why 1 mole of this gives you 2 moles of hydrogen ions. So that's why 1 equivalent of that is 2 equivalents of this. Now, what's the value there? Well, in terms of concentration, well, phosphoric acid, let's go ahead and do that one too. If you put this in solution at 1 molar concentration, here, each one of them, 1 molar, then what you get out here is 1 mole here, actually 1 molar concentration there, 2 molar concentration there, 3 molar concentration there. So the equivalent concentration of hydroxide of hydrogen ions is 3 times the molar concentration of the acid. What value is that? Well, the value is based upon the net ionic equation for an acid-base reaction. The net ionic equation for the acid-base reaction is this. Right? Everything else is spectators. That is an acid-base reaction. So if we know this in terms of equivalence, it doesn't matter what it came from. You still get the same reaction, and the concentrations then become manageable. Because this could have come from here, could have come from there, could have come from there. If we make it in terms of equivalence, then we can do the calculation no matter what the acid base is. Now we're introducing another concept here. I know it may twist your head around. But the milli equivalent is a useful term. It's just 10 to the minus third equivalent, right? Milli means 10 to the minus third, a thousandth of. Now, why would we want that? Well, as it turns out, if you know the concentration of, say, your acid here, like that, and say it's a 10th molar, but you have 50 milliliters of it, and then you're going to react it with something else. Well, remember the definition of molarity. Molarity equals moles per liter. Right, so the volume has to be liters. But instead of changing milliliters to liters and getting number of moles, why don't we say 50 milliliters times 0.1 molar, and that equals to 5 millimole, and since it's from 1 proton, that's also equal to 5 milli equivalents. Okay. Now, that you don't stop there, because if you have to convert back to concentration, now if you divide millimoles by milliliters, you get molarity. And if you divide milli equivalents by milliliters, you get molar equivalents. Okay, so the takeaway is, if you have concentration of an acid, a base, or salt in terms of molar, then you just need to know how many dissociations occur. We could extend this to salts. Right? So if you say sodium chloride in solution produces sodium and chlorine, if you have 1 mole of this, how many equivalents of ions do you have? You have 2 equivalents, because it dissociates. All right, let me get this back lined up. There we go. All right. So this is just an expression of electrolytes in the blood plasma. Sodium's the major one. Then you got a little bit of potassium and the rest. Those are positive ions. Negative ions, chloride and bicarbonate, HCO3 minus. Those are the major negative ions in your blood plasma. Chlorine for various reasons we can't go into now. But bicarbonate is essential for the transport and expulsion of carbon dioxide from your body. In other words, when cells respirate, they take organic compounds, and the end products, among other things, are carbon dioxide and water. Well, the water just becomes part of the cell matrix, the solution. But the carbon dioxide has to be getting rid of. So there's a buffer, there's a transformation that occurs with the aid of enzymes to convert carbon dioxide into carbonic acid. And one of the products of carbonic acid is HCO3 minus. It dissociates 1 proton. And that transports the carbon dioxide from your cells through your blood to your lungs. And then another reaction occurs in your lungs that converts all that to carbon dioxide, and you blow it out. So this is a major electrolyte in your body. And then some of the others are minor. Okay. All right. Yeah. I'm out of time, but I'm going to finish, of course. You knew I was going to say that. The concentration of calcium ions present in the sample is 5.3 milliequivalents per liter. how many milligrams of calcium ion are present in 180 milliliters of sample. Okay? The solution to this problem is really dimensional analysis. So you're starting with 180 milliliters of solution. Okay? 180 milliliters is how many liters? Since we have, our expression here is 5.3 milliequivalents per liter, then we're going to change that volume to liters. And by, let's see, yeah, there we go. Cancel the milliliters, then cancel the liters. Now we've got milliequivalents as our unit of measure, times 5.3 divided by 1,000 times 180. And now we want to convert milliequivalents to equivalents. So milliequivalents, here we cancel those two, and the ratio is 1 per 1,000. Right, now we have equivalents. And that 1 mole of calcium ions is 2 equivalents because of that charge right there. Okay? There we go. So all of this together, well, let's see, I haven't finished yet, have I? That gives you moles of calcium, because we're talking in terms of equivalence first. And equivalence is based upon charge. Remember, HCl is just one charge, negative charge. H2SO4 is 2 charges. So that means for every one of these, you get 2 of those. For every 1 charge here, you get 2 charges there. So that's what the equivalent is based upon, is the charge. So now we've converted to moles of calcium. Now we can use molar mass to convert calcium to milligrams. So we got these, we're going to convert back to milligrams, and now 19 milligrams of calcium ion are present from this data. Okay. So while discussing mixtures of ions, a chemist focuses on ion identity and amount rather than the compounds that supply the ions. That's a useful technique because maybe you need to conduct a reaction and you don't have the chemicals on your shelf. But if you have something that will provide the ions in equivalent amounts with the spectator ions, then you can toss them out. Then you can complete the reaction. The concentration of ions is specified using the equivalent units. Now, that doesn't mean that you cannot conduct the reaction using molarity exclusively. But if you do that, you need balanced equations and you need conversion factors from the balanced equation. Right? You can still do it, but this is a shortcut method. If you express values in terms of equivalence, then you can get there with a couple of fewer steps. Okay, what's a titration? A titration is a neutralization reaction between an acid and a base. Actually, titration is a generic term. You can do all kinds of titrations. The basis of a titration is equivalence. You know this one? Let's see. You know this one? But this one's unknown. You don't know what its concentration is. If you titrate it with the known, then you can make a conversion of units from one to the other, and you find out what the unknown is. So acid-base is just one type of titration. You can do all kinds of different titrations. You just need to understand the balanced reaction in order to interpret the data. So in this case, it's a neutralization reaction where you completely react an acid and a base in a measured volume of a known concentration of 1 so that you can discern the concentration of the other one by the amount, the volume of the unknown that you add to the known. And for acid-base reactions, this is the equation. That much acid, that much base gives water. This is what a setup would look like. Right? You have this device here called a burette, and it's marked off in volume measurements. Typically in our lab, we have a 50 milliliter capacity burette. Now you'll notice if you look at them closely, and probably if you've done the lab where I did a titration, I've expressed that to you already. The small measurement numbers are down here. No, the other way around. Small measurement numbers are here, large measurement here. The reason for that is that the burette is designed to deliver a volume. So if you start at 0 up here and you go down to 10, that's 10 milliliters delivered through the tip. You put a known volume of, for instance, an acid in your container, and you know its concentration. So that means if you know the concentration and you know the volume, then you would know the number of moles of acid. Okay? But this is unknown, correct? You put the unknown down at the bottom. So this is unknown. But in the burette, you might have base of a molar concentration. You know that one. So all you have to do is deliver enough volume of base so that these two are equal. If these two are equal, then you know that that value is known, this value is known. You calculate the molarity of your unknown. Now, when that happens, when acid and base are exactly equal, number of moles, that's your equivalence point. Okay, how do you know where the equivalence point is? Right? If they're both colorless and you don't have a pH meter with a probe in it to tell what pH it is, then you don't know what the equivalence point is. If you measure the pH against added increments of titrant from your burette, then you can plot it and you can find the equivalence point. But it's more convenient if you have a lot of them to do, and I've done hundreds at a sitting. It's better if you have some indicator that'll get you very close to the equivalence point. And it's a visual indicator, like a color change. The color changes when you're close to the equivalence point. It won't ever be exact. But if it's close enough, then the calculations will be adequate and accurate enough for, as they say, government work. So here we have a pH indicator that changes color from yellow to purple. You just add enough, and once you reach, and when you get close to the equivalence point, we call the end point when you're using an indicator, then you need to slow down and drop by drop. You don't want to overshoot it. If you overshoot it, that one's throw out. It's no good. So you can you can actually do a test titration and get close and throw that one out. Then you know how much you can add to get close, and then you slow down and drip, drip, drip. That speeds things up. So when you reach that color change, then you measure the volume that was delivered and do your calculations. So with this particular problem, let's see, how am I? Yeah, we're pretty close. With this problem, we have sulfuric acid and sodium hydroxide. How many moles of sodium hydroxide would be required to react with 1 liter of 0.5 molar sulfuric acid to reach the end point? All right. If we use that reaction, then we need to focus on equivalence. I'm going to show you 2 methods. One is this one, where we have equivalence. Okay. So if this is derived from sulfuric acid, then we have 1 liter and half molar. If we multiply those 2 together, we'll get moles of sulfuric acid. 0.5 moles of sulfuric acid. How many equivalents is that? It's twice that. So we have 1 equivalent of acid. Okay? So that means we need 1 equivalent here. Exactly 1 equivalent. What is the equivalent ratio of sodium hydroxide? It's 1 to 1. So 1 equivalent equals 1 mole. Exactly 1 mole. Okay? Now, this equation right here is based upon the actual balanced equation for sodium hydroxide and H2SO4. I'll show you that one. If you use equivalence, you can do it in your head. But if you're going to react, let's see, sodium hydroxide plus H2SO4, then that reaction is going to be, you're going to leave yourself with sodium sulfate and water, right? Salt and water. To balance this equation, we need 2 sodiums here because that's 2 minus and this is 1 plus. So now you need 2 sodiums over here. So 2 hydroxyls, 2 hydrogens yields 2 waters. So there's your balanced equation. Now if we know 0.5 molar of that, then, and we want to convert it to moles. Let's see, what do we have? 1 liter. Then we get 0.5 moles of H2SO4. A bit messy. There we go. Now we need a conversion factor that will give us moles of sodium hydroxide. So what's the conversion? H2SO4, sodium hydroxide. So we have, for every one of these, we have 2 of those. So 2 times that is 1. I think that equation is a bit off. This should be 0.5 moles of sulfuric acid right there. Okay? When determining the concentration of an acid or a base, a blank is performed using an acid-base titration is performed using an acid-base indicator to visualize the desired pH. So acid-base titration, acid-base indicator. There you go. Is that the last slide? Oh, there are a couple more slides. Okay. A solution containing a hydronium ion, concentration of 9.34 times 10 to the minus 8. Right? So that's less than 7, so it's basic. Has a pH of whatever. Do the calculation. 9.34. 10 to the minus 8. Right? Then we take the log of it and then change the sign. Is 7.03. Right? So that's right. Each one of these is 7.03 is good. And is considered to be 7.03 is basic. Right? So it's either this one or that one. And has a hydroxide ion concentration of what? Well, let's do it the easy way. 7.03 subtracted from 14 is 6.97. So now we need 10 to the minus 6.97, which is 1.07 times 10 to the minus 7. D. Oops. Nah, it's not neutral. It's close, but it's slightly basic, isn't it? Right? Okay, 6 of 1. Maybe I ought to move that down here. All right, I think this is the last problem. Yeah, this is the last one. Concept check. All right. Let's see, get that back on center. 25 milliliters of acid requires 14.8 milliliters of 0.351 molar base for complete neutralization. So we have, let's see. "25 milliliters of acid requires 14.8 milliliters of base at 0.351 molar. What's the molarity of the acid? Well, notice I put this note in here. In this case, you have to assume that they're both monoprotic and monobasic. Right? Otherwise, you don't know, because we weren't given equivalence. We were given molarity. Right? So in this case, we have to assume that there's only one of these and one of those. Well, the rule now is that the moles of acid equals the moles of base. So what's the moles of base? Well, let's use millimoles. It's easier that way. So molarity times milliliters is equal to millimoles. 14.8.351 is 5.19 millimoles of base. 5.19 millimoles. So that means we have 5.19 millimoles of acid. Well, millimoles divided by milliliters is molar. Let's do the calculation and then I'll prove it to you. .1 rounded off. Yeah, 2.08. So 2.08 molarity is your acid concentration. All right. Now, how can I say, well, here's one proof. We can use molarity here if they're monoprotic and monobasic. Otherwise, you have to use equivalent measurements. But otherwise, this works. Or you have to use a conversion factor. If one of them is di or triprotic and so forth. But why can I take millimoles and divide by milliliters and get molarity? Well, let's go from the definition. I'm already over, so I'm just going to take my time. What's the definition of molarity? It's moles per liter, correct? All right. Well, let's say we divide this one by 1,000 and make it millimoles. Let me change that. This is moles. Moles per liter. If we divide moles by 1,000 and make it millimoles, okay. So these two are equal to millimoles. And we divide this one by 1,000 and make it milliliters. Well, where does this one go? Well, when we resolve it, right, the denominator of the denominator is the numerator. So this one goes up here. Correct? What happens? They cancel each other out. So this expression is exactly equal to that expression. And that makes it easier to deal with calculations if you don't have to change back and forth between milliliters and liters, because most lab glassware, with a few exceptions, is calibrated and marked in milliliters. So it's easier to deal with that unit of measure if you know what you're doing. Okay, that's it for Chapter 10. And we'll come back next Friday. This is Friday, the 30th of April. We'll come back on the 6th, is it, of May? No, 7th. 30th. Yeah, we'll come back on the 7th of May and do a review on chapters 9 and 10. And then the following Friday, well, that'll be in the final exam week. So you can take the exam anytime you want that week. And that'll be the end of it. All your exams, all of your laboratory reports. Right? If you haven't turned in all your laboratory reports, don't wait till the last minute. Because if I run out of time, if everybody turns in their reports at the end and I run out of time, then first come, first served. And I'll grade them in order. If you run out of time, even though you turned it in, you'll get a 0. So if you push me to the limit, then you're going to lose. Okay, that's the end of this lecture.